beyond the meniscus, you have the liquid moving in this direction and the vapor moving in this direction. So this again means when I do an analysis, I have to incorporate this area of cross-section variation in the model. That is the most important thing that I do when I analyze a micro heat pipe in comparison to the conventional heat pipe. There, I have definite areas of cross-section which is true, the same everywhere because of the presence of the big structure, whereas here I have to formulate this problem as a variable area cross-section problem. So when I formulate something with a variable area cross-section problem, it becomes, it creates differential equations which are equations with variable coefficients. Numerical solutions are brought for these equations with variable coefficients. So I have to know what is the length dependence on the cross-sectional area. Then only I can incorporate in that. This can be done by looking at the geometry of the meniscus inside the heat, depending on what is the cross-section of the heat pipe. I hope you understood the difference between this and the conventional heat pipe design. Let's come to that a little bit later. So I said that only a small quantity of heat can be handled by one micro heat pipe because it's a very, very narrow channel, small channel. And what I use if I have a considerable quantity of heat to be removed, like if I want to cool an electronic chip of size something like 2 cm by 2 cm, which produces a heat flux like say 2 or 2 to 4 watt per centimeter square. So this is a considerable quantity as far as the heat pipe size is concerned. I cannot do it by a single heat pipe. So what I do is I make an array of heat pipes, a number of them. It can be easily made. Say this is a cross section. It's so simple. I take one. Say this is a lower plate. I take one lower plate. See, this is the lower plate, and I put grooves on it and cover it with the upper plate. Like this. This is a cross sectional view. So I have a number of passages through them. So these are all heat pipes. One passage, you know, these dimensions are all millimeters. 0.65. The total thickness is 1 millimeter. So it's just like your scale, your centimeter scale that you're using. This is a very thin thing, which is a heat pipe, which contains so many passages inside. So if I'm using these geometries, I can arrange so many of them. For example, I have a case like this. It looks like a heat pipe. Okay, the total length is only 124 millimeters, around 12 centimeters, and the thickness is 1 mm. I have 40 channels inside. If you cut it like this, I can see 40 channels like what I have shown inside. So this is a micro heat pipe array. Now I have the heat pipes all arranged. See, I can have my electronic component sitting over this. You can extract the heat from it, and then I can have a cooling effect here. I can have, say if I have an adiabatic section, I can have an adiabatic section. I have the condenser section, I can have circulating fluid over there to take away the heat. So the advantage is that this is very easily reusable, and then you can also attach to an electronic component. More than that, there is another advantage that I can fabricate right on silicon. Okay, so I can have a chip with a tail, extended tail, which the chip manufacturing people can make for me, and I can have integrated channels there on this straight away at the manufacturing stage, so that the heat sink is integrated onto the electronic chip. So what is the advantage? I don't have to stick anything over the electronic device, and I don't have this confounding problem of contact thermal conductance coming up there. So my heat pipe also, my heat sink also can be part of my electronic device. So basically some of these miniature systems like this were initially envisaged, or rather conceived, just to overcome the problem of attachment of such devices on electronic systems, so that these can be directly fabricated on the material that we use for the electronics, so that it can be a heat dissipation device integrated onto the electronic system. It's a fascinating idea. So some of these have also been developed in some of our laboratories where you worked before, and an example is this. This may be in silicon, or this may be in copper also. I can make it on copper and attach it on the surface. That is possible. For